Well, welcome to week 5. This is simulation 1 of 2. Next week, we will carry on with the story of Make a Pie and Simone Tortzier and Marta Fazi and what they're up against and well, about any business is up against. Next week, we will have more of a story of how to manage losses. This week, we're just introducing the notion of simulation, which is probably the single most useful tool I have found in my work. And without further ado, let's get right into that as I share my screen. And yes, it's 10:10 in the morning. Here we go. We have the story of chance. We're going to look at how we can formulate a model. That's the piece of pie, please. We're going to take a brief interlude into putting a little bit more complicated structure, correlated variate structure, into fairly simple model of waiting times with a solution, of course. And then we get onto the simulation itself. And as you can see, yes, I'm using matrix algebra. I don't know if anybody ever told you that we should, but that you should know matrix algebra. That's not the point of this. The point of this is as much documentation of a standard algorithm and then applying it. Excel or Bust actually does the application of this, and we will walk through this in a separate session a little bit more rigorously, because the idea here is a powerful one. How can we take two independent random variables and correlate them, and then use those correlated variables as the seed, the foundation, the random numbers, if you will, in our simulation in the case that we're going to be doing waiting time. And as we move through this, we are actually creating something I call the eatery robot. And we will be literally in our workflow creating parameters. Now, when we go out and actually in the field and estimate timings, this might be at a vaccination center, for example. It might be a launch of a new product, acceptance rates, whatever the situation is. We first always want to put together a generative model, and thus the name of this week, Generous Generation. We will waste simulations, a la George Gilder. The main course here, this is the ultimate piece that we're going to try to get to. And then we're going to do some basic exploration where we will build in Excel something that Excel doesn't do very well anymore. I used to do this quite well. It's create histograms. I tend to not like the bar histograms because they're a little bit busy visually, but you'll see how we build it with all of the formulae and all of the gory details here. And finally come up with this. This is what we're going to come up with. And yeah, this is our work product. And of course, there are always next steps. I will be using a bit of algebra through this as well, as you can see here. Don't let this dissuade you. Try it. It's logic. Algebra to me is logic. It follows logical rules. All the things that we've been learning probably since 6th or 7th grade forward can be put into here. There's even a reference to a Philip K. Dick novel in this one. All right, so let's get back to the top of the heap here. And we start with a story of chance. The Monte Carlo simulation, Monte Carlo is actually the government code name for top secret project during and after World War II, till about 1947, 48, about the same time. that George Danzig and Ken Marshall in the U.S. Air Force came up with the simplex algorithm that we, of course, know and love from weeks prior. Stan Ulam was a Polish emigre to the United States, and he was asked to work on the Manhattan Project. He's a mathematician, a physicist, a wide range of interest, hundreds of papers with lots of people. Amazing. He got sick one day, needed some surgery. And during that time, I think it was about 43, 44, 45, around that time, toward the end of World War II, he was playing solitaire, and being a mathematician, being of the ilk that he worked with Albert Einstein and Enrico Fermi. For example, Hans Bethe invited him to the Manhattan Project. He became an armament maker. Thermonuclear weapons was what was being made in the project. But go back to his sickness. He got bored, was playing solitaire, Klondike version, of course. It's a typical one. And he was figuring out how many hands. Well, it's 52 factorial is the number of hands. That's something on the order of 10 to the 67th power. And he's going, there's no way I can play all of the hands and figure out all of the ways in which I can possibly win. So he said, wait a minute, let me take a few hands that I know I can win and a few hands that I know I can lose, and let me record those. Let me take a few more and a few more, and it's just win or lose. It's a binary situation. It's a 0 or a 1, the same thing that powers the computers. The most basic data we have is 0 and 1, and everything else can be built off of it. He knows this, but he goes, let me figure out the frequency of wins. And that's what's in the reading here. The probability of a win, what is the standard deviation? He's going toward the standard deviation because he wants to see how many hands must be played to get a good idea of the probability of a win. That's what he's looking for, the probability of a win. You want to know what the odds are of winning when he plays the next hand. Pretty high, actually, for experienced gamblers, very high. We used to, when I worked at Deloitte and Touche, one of my jobs was working the casinos. Well, I'm not allowed to play in the casinos, probably still. They were our audit clients. Nick Tomasino was one of them. And he's an alum, a 1979 alum of Manhattan College. And we'd have to go in and verify various journal entries in the accounts as auditors. I'm not an auditor. I was a specialist who worked with auditors. And I actually had to put a value on certain operations, help to put value on, for example, licenses. When they would license their operation to a riverboat or something like that. Fascinating. Not my cup of tea, but fascinating. And we would also have to look at the odds. We would take samples of craps tables and blackjack and others to see that there were fair games, or else we could not provide a unqualified opinion of the results of the operation. So we did all of that. We calculated things like this formula that you see here. And I'm belaboring this because the story is the interesting story. If we go and actually look at this and start to figure it out, as you can see, this sketch relies upon a definition of the probability, and it involves the number of trials, runs. These are the individual samplings that a Monte Carlo does. And the whole point of this is as n gets larger, the standard deviation, take the square root off of this and square both sides, the variance of that probability gets smaller and smaller. That was the point. My gosh, it was so simple. This is foundational statistics, foundational probability as well. So that's all it took was foundational thoughts and a insight producing situation like boredom. Now he talked with Johnny von Neumann, and this is the other takeaway, who had been building the Eniac. Look up the Eniac. The Eniac computer, I believe it was an IBM collaboration, 17,000, not transistors, not integrated circuits, vacuum tubes. This is the old vacuum tube that you hear crackling when you turn on a TV circa 1970. We had a black and white Zenith 19-inch. Very happy to have it. It was more like an oscilloscope in physics class in high school than anything else. But a lot of this story is told by Thomas Haig, which is in the readings. But the point of this is it took technology to implement this idea. People were literally called computers. I was a computer once for a small project in Knowles Atomic Laboratory in high school. I had my dad's slide rule, and there was a block of 25 of us, each doing parallel calculations. It was almost like a competition. And they had a form that you filled out, you did the computation, you put the number in, they collected it, somebody collated it, and it was all logarithmic, so you could add them up. And then take the anti-logarithm of it and calculate the probabilities. That's what the experiment was about. And we were fairly accurate. They compared it to a computer that was running a new program at the time. This is the mid-60s, called Fortran, Formula Translator, another IBM thing. So the takeaway here is simulation takes off in the late 40s because of innovation in technology. Okay. Now, another takeaway is hopefully there are peaceful uses. These folks used Monte Carlo to design thermonuclear weaponry. Okay, that is not what we're going to be doing. We're not arms dealers or armament makers, but Leonardo da Vinci certainly was, and he finally retired from it as well. Made very, very creative ways to kill. Lots of different interactions. We're going to be looking at a 20 eatery. We're still into eateries here, and eateries, cafes, lunch counters, vaccination sites, testing sites, grocery lines, bus lines, all have this notion of waiting in line. And how long do you wait in order to get a result? How many visitors does Target need to go through its doors to produce a certain number of those visitors, percentage of those visitors who will actually transact, and at as high a transaction per customer that dollar value that they can get. Okay, so the model that we're going to be building here comes out of a request by Tortzier and Fozzi, because what they really wanted to do was meet and greet people. Yes. Customer relationship, sharing their passion for veganism, I suspect, with people even in the Bronx. Now, you will find veganism in very interesting places in the Bronx, usually in the Jamaican communities. There's a very strong Jamaican community in the northeast Bronx, around Baychester Avenue, for example. Um, this is the market they want to tap into. Okay, they think they can make money at it, and making money at it for them is money to plow back into the operation and do more. Okay, that's the idea of money to them, of income to them. And what they wanted to do was, okay, let's start this process. They know waiting times are extremely important. We all go in Starbucks and places like that. How long do you have to wait to get served? And then how long do you have to wait after you get served to have the product delivered to you? The coffee, the donut. Go to Dunkin' Donuts, same thing. Grocery lines, the same thing. Okay, so anything that deals with customers on the fly, quite literally, will have lines and waiting in situations like this. So they want to understand that a little bit more. So we devise an experiment. We create a robot, a model robot, and we program it to go through and sample average waiting times. And the other thing that Torsier and Fozzi noticed is that time of day might matter. A morning shift versus an afternoon shift, depending upon the location of the eatery, the facility. We also find that with vaccinations. Some people are able to take morning vaccinations, so that gets more congested, and sometimes it takes longer. And as opposed to afternoon, because of work or whatever, it's a little bit lighter, less congested, and certainly the center I have gone to for my vaccinations at Edenwald Senior Citizen Center, which is now open to the public. In general, you don't need an appointment anymore. Is the same behavior going on. You have literally two distributions mixing together. And that's an important part of simulation. We're looking at different behaviors and we're mixing them. So here's a simple model. With the simple model, let me blow it up here a little bit. And we're going to locate this model in the cerebral cortex, the matrix of the robot. It's going to be a computer, obviously. We have eateries indexed by I. We're going to use 20. I equals 1 to 20. And it's a simulation. This is a thought experiment. It's not reality. Reality is us going out there and actually measuring. But this little tabletop experiment will help us do this. Next week, we will do a very similar tabletop experiment with loss. And use a very interesting distribution, which is typically not taught. It's what we call a left pocket distribution. The right pocket is normal distribution, or the t distribution, or the chi-squared distribution, or the beta distribution, or the gamma distribution. Those are right pocket, or even Poisson. The left pocket will be the generalized Pareto distribution, because it handles tail events, and that's something we want to deal with next week. This week, everything's going to be hunky-dory and within the normal corpus body of normal things happening. Okay, nothing terribly rare is going to happen here. But we're going to sample in our mind with our robot is going to sample the average waiting time for the morning, which will be alpha, and the average difference from the morning that the afternoon is. Now, beta is negative if alpha is 3.5 and beta is -1. And A is an indicator saying 0 in the morning, 1 in the afternoon. Then all we're left with is alpha. Alpha plus beta times 0. If it's an afternoon, it's alpha plus beta. So it's just alpha, one distribution of behavior, a morning distribution of behavior, or it's afternoon and we get a mixture of morning and a difference from the morning in the afternoon. That's rich. That's a rich model. And so go through this idea. Uh, 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 yeah, especially the covarying of intercepts and slopes and why that might happen. Well, it tells you why it might happen here, but imagine you switching lines at a grocery store when it's congested, which is usually mid-morning, versus when it's not so congested, mid-afternoon. And the butchers have already cleaned up and they're gone, all right? So nobody will be there. And the waiting line at the cold cut counter is all of a sudden, it's quiet. They're taking a break. They haven't been slammed. Okay, that's the kind of thing that you think through as you think through this situation. And in order to understand that covariance, we need to get into some maths. Uh, uh, what is a covariance? It's the expectation of two variables. And if I just get a board going here, it's a nice Microsoft product. And create a new one. So we have morning and afternoon. And let's get the pen working here. And it doesn't seem to want to work at all. Okay, so I can't use this. Maybe I can use this. And the system doesn't want to allow me to do anything today. Okay, now maybe it's activated now. So here's the morning. There we go. Got the technology to work finally. Here we have the morning. And here we have the afternoon. So this is the time of day model. And in the morning, we have a distribution. This is going to be fairly wide. Its mean is alpha. And in the afternoon, we have a distribution that's a little bit tighter. Does that mean it's more predictable? Not necessarily. And its mean is beta. So for example, if alpha is 3.5 and beta is -1 and A equals 0, then our model says the average is equal to alpha plus beta A for a particular eatery. And the beauty of this is we can do as many eateries as we want. I just picked 20 out of the hat, pretty much, following a model of cafes by Richard McElreath in Statistical Rethinking. Okay. Now all the cards are on the table. this will be equal to 3.5 plus beta times 0, or 3.5. Now, if it's the afternoon, mu is equal to 3.5 and the technology is gone again. There we go, finally got that back again. Plus beta, and by the way, beta is minus 1 times 1. And this will therefore be equal to 3.5 minus 1, or 2.5 is the afternoon schedule. It's alpha plus beta. So we're actually combining these two into a morning alpha. Okay, it looks like this. And whatever these two literally convolve into, which could look a little bit like this. That's alpha plus beta. This is called a mixture of distributions. And it is the core of every single machine learning and AI procedure out there right now, where they just mix Gaussian distributions, normal distributions, because it's different behavior distributed differently. And that's a key takeaway of this whole analysis. Okay, the rest of it is quite mechanical, but this is the thinking behind it. It's a very simple indicator model that I think I have used like hundreds of times, just to build a little toy model to get people conversing in the right direction, but with guaranteed logic. The logic of the model is always the logic of the model. It always works, just like that variance of the win-loss, P times 1 minus P over N. It always is that number. And that's a deduction, and deductions are always guaranteed. Getting back to the model here, I have some kind of relationship now between A and B that I need to put into the simulation. And the correlation rho is the coefficient of correlation, is the correlation between average wake times in the morning and the difference beta in the afternoon. 3.5 average minus 1 in the afternoon. We're going to use a standard deviation for alpha of 1 minute, and the standard deviation of beta, the difference between morning and afternoon, as half a minute. Okay, that's difference. The way we always start this is the idea of some uncorrelated variables. These things are totally random. They're totally independent of one another. So these variables, if I can bring up the palette here. Well, that's interesting. It used to be supported as of about an hour ago. Okay, we'll have to investigate that bit of technology. Technology is a challenge today. And we want to transform this variable, these variables X, using some transformation process, and that's going to be another matrix, into correlated variates. So we want to put an information structure in these variates. That's the point of this, and it'll be such that, and to check that, we say that R, the one row 1, which is a transformation matrix as well, must equal however we operate on, let's say, a rand variable in Excel. You run a rand variable, it's going to give you a number between 0 and 1. If you run a normal rand variable, it'll still give you a number between 0 and 1, but those will be normally distributed, but still random. But if you ran two of them, they're totally unrelated to another. And we want them to be related, okay? That's the whole point of the simulation. And these are the mathematical realities I have to deal with, and I'm going to make you deal with it as well. So in order to do this, L and L, I'm going to use a trick of linear algebra that says I can decompose any square matrix into a lower triangular. Look at the little triangle that's formed here, L11, L21, L22, and an upper triangle. Okay, any square matrix can be decomposed into these pieces. And if I do that decomposition and then multiply them through, I get this interesting, as I call it, matrix. So you can see it's L11 times L11 plus 0 times 0. That's the entry in that piece right there. L11, then I go down the other column, times L21 plus 0 times L22. That's the entry here, and so on. Okay, it's matrix multiplication, which is just a multiplication rule. That's all it is. There's nothing magical about it, but it's a set of rules that will work every single time. But now if we match up these L11 squares, L11, L21, L11, L21 again, and L22 squares with the original information matrix that I'll call this R. It's almost an information matrix. If we match them up, just simply match the one up with this. That's pretty straightforward. L11 squared equals 1. Take the square root. It's still 1. So we now know that L will be this new matrix. L11, the lower triangle, will be 1. We can formulate that. L11, L21 equals rho, implies L21 equals rho, because we know L11 equals 1. See, love this. Now, somebody did this and actually made it into an algorithm. It's called the Cholesky algorithm. Look up Cholesky. Cholesky, it just rolls off the tongue. Which tongue is that? Well, there we go. It's a Cholesky distribution and transformation, and it's given all sorts of names. But without it, we can't do more than one random variable at a time with any kind of notion of it being even close to reality. Most things in the world are conditional and correlated, and that's our job right now. So there's Cholesky. I believe he was an artillery officer. Neither here nor there, but now we have an algorithm. Now we have a matrix that, when applied to a vector, it's just a 2-entry vector of independent variables, will, when multiplied through, give us 2 new but correlated, not independent, dependent variables. Now we're on a path for Monte Carlo. Now we can simulate. And here's the rest of the story that you could read. X is a vector of, okay, this is just the rand function. Okay, what's the rand function in in Excel, it's just this function here. So each X will have this as a start. Every time you type in rand, a different rand, look, you get a different random number. Now we want to take these two numbers, which are random, okay, and pre-multiply them. So let me grow this up here a little bit. Let's see if we can. The technology is having a tough time. Zoom does not want to work for this, but that's okay. I think you can just about see this. Let me pop this into a new sheet. See, it's even a new one. It's a very volatile function. Now, if we set rho to be, let's say, minus 0.7, and of course, we're always going to use good spreadsheet practices and designate this as a named range. And it's called rho. You can see it's called rho up here. It worked. Rho here is just whatever in the name manager. And my penchant for, I am not this way in the rest of my life, believe me. This kind of drives me nuts. I have to put this into a format, okay? I just have to do it. Okay, so here's a vector. We're going to call it X. And here's a matrix. We're going to call it L. And the first, let me put a box around that matrix L. The first entry is 1. Second one over here is 0. This one is rho. Not that row, this row. There we go. And the second one is the square root of 1 minus rho squared. I use a square root function. It's a very fast one. 1 minus rho squared, close parentheses, and we get that. Now, is that what we had over here? Yes, it is. 1, 0, rho square root of 1 minus rho squared. See, I've done this so many times, and I've had to build this sheet in front of a client so many times without them really seeing what's going on. They're going, "Oh, that's interesting. What's that about?" I'll tell you later. You kind of remember most of these things. And this 1 minus rho squared and the square root of that also will come up in a model that we can build next week that I want to introduce you to. Get you ready for statistical decision making, which will be week 7 with all the stuff that we've been doing. Okay, well, you'll see this come back. It has a life, a very interesting life. Now, what is Z? Well, Z, oh, look at that. Every time you put something in, everything changes. Okay, so this is the symbol notation here. Bold this up. Now, Z, we want to be correlated. How do we get that? We do this. Now watch carefully, sleight of hand. I know that Z is going to be exactly the same shape as X. It's going to be a 2-row, 1-column matrix, otherwise known as a vector. There we go. I select that area. I then use equals mmult, matrix multiplication, open parentheses. The first entry is the L. You know, even better, you know what I should have done so that you can actually see this working is call this L. Well, let's do that too. We're not going to do it this way. We have to do it as a defined name. Just call it L. The comment on this will be Cholesky transformation matrix. Okay, now we have L. See, it pops up right here. And of course, we're going to call this, of course, X. And that's a vector of two independent random variables. Figures are working fairly well. Good. Now that's done, and we can see it shows up as an X. Now, Z, it will be this space. We might as well give it a name right now, Z. And this is also a vector of correlated random variables. Now, it's going to be very important when in what comes up that these correlated random variables are being drawn from a Grecian urn. That's a uniform distribution. Every single draw is equally likely for X. That's the random draw. And Z's will be equally likely as well, but they'll be correlated with one another. I pick one Z. When I pick another Z, it'll be negative 0.7 correlated with the previous Z. Okay, that's the idea of this whole thing. Okay, so let's, there we go. Now it's official. We've selected this. And now I can use an array function equals mmult, matrix multiplication, open parentheses. This is the beauty of this, L, comma, X. Close parentheses, do not press enter yet. Keep your left pinky on the shift. Maybe your left thumb on control now, then press enter. And it's done. Now notice the first one is going to be the same because it's 1 times 0.35 plus 0 times 0.04. So Z1, the first one, is always going to be the same as X1. But Z2, notice coming up negative, that's positive, that's negative, will be minus 0.7 times 0.35 plus 0.71 times 0.04. And you get a negative 21. Now, can we find the correlation of these two? Yeah, we can. We can do this. X and Z. It's not the correlation we're looking for, but let's look at it anyways. They're perfectly correlated. And that's a very interesting artifact. Okay. Now, the problem is we want to run this a gazillion times. That's word of the week for a lot. We're going to run it 10,000 times. And I'll show you that spreadsheet in a moment. So we just proved something here, that all of this works. R is equal to L transpose. Again, I always try to do this in Excel or R or Python or something. L transpose. So let me see if I can recover R. Now R was 1 on the diagonals and row off diagonal. That is the shape and the content. So 2 by 2 is the shape, 2 rows, 2 columns. And we'll call this R. Okay, so we have R, and of course I'm always going to name these. And this is called the correlation matrix. And it'd be nice if I could spell this. I can barely see it. There we go. I think that's correct. Good. And that defines that. The syntax of this name is not correct. It starts with the letter. I want to call this R. And it doesn't like it at all. Doesn't include a space. It just doesn't like it. And you learn about this in Excel. Okay, this probably needs this, an underscore after it. There we go. We're going to call this R underscore. It's ornery sometimes. All right. Now, the promise was L superscript P. Now, the superscript is exchange rows for columns. It's a transpose. So can we compute this? Absolutely. We can do matrix multiplication of L and the transpose of L. But if we do that, we know it's a 2 by 2 times a 2 by 2 will give us always a 2 by 2. A 2 by 2 shape multiplied by a 2 by 2 shape will give us 2 by 2. Right? That's a guarantee. And the way we usually think about this is row times column, row times column. Now 2 by 2, 2 by 2. Okay. Gives us a 2 by 2. That's the old trick from high school. In the LX situation, what did we have? LX equals Z. We had a 2 by 2, and X is a 2 by 1. Get rid of that. The result will be a 2 by 1. Okay, these are little tricks of the trade. The carpenter getting the exact cut for a roof. If you're off by 1/32 of an inch on a roof, and you see carpenter's squares are marked off in 1/32, that whole roof will ripple. Well, they have tricks for not only measuring, but cutting. That's what we're doing here. I consider that a trick. So here's L. Actually, here is L. And all I have to do is create the result here equals M mulp L transpose of L, yes, we have that as an array function. Oops, we don't want to have that. What the heck is going on there? Okay, so that's just crazy. Okay, now we're going to try this again. Oh, 1 to 14. I'm finding that's been happening a lot too. So we just want to put L in there. And then Shift, Control, then Enter. And look what we get back. So we know our math is working, even though Bill's fingers aren't working very well. My goodness. And we just verify the Cholesky this way. Because that was what we started with. R, the correlation matrix, is equal to L transpose, where L is this lower, that's what L really stands for, the lower triangle, times its transpose, which is the upper triangle. Oh my gosh, you've got it all. All the secrets are out. Okay. So now we have that, and here's a little sketch of it, and here is an example of it. Much what we just did, with all of the details of all of this. So try pulling this together yourself. When you do, call all of this area C2 to N3. Call that whole area calculation. Give it a name. Then we go over here to the right. Okay, so we're going to do the same thing here. But I'm going to call this calculation. Now, I'm going to call it calculation because I'm going to call up a program that I wrote quite a long time ago. And Excel refers to these as regions. Now we're going to actually build a subroutine and recalculate this a bunch of times. Notice I didn't say gazillion. Okay. And over here, we're going to create an interface of X1, X2, Z1, and Z2. I don't have to do all of this, but I do it because it's easier for me to see what I'm doing. Okay. And that's just a label. And we're going to pull out whatever is in this cell, that's X1. We're going to pull out, I could use a transpose to do this as well, whatever is in X2. Same with Z, Z1, Z2. And we're going to label this range interface. And I'm going to say that it mediates variate recalculation with something that I haven't done yet, with a record of the simulation. We're going to create another region right here, and it's going to be equal to, it's going to be started off this way, but we need to declare an area. There we go. We need to declare an area where we can start recording. Now, we want to record this result in the next row, and then tell the sheet recalculate, and then record the next result from the interface in the row after that, and so on. And we want to do this the gazillion times equals 10,000 times. Okay, this is Stan Ulam's Monte Carlo machine in Excel. Same idea. They refined that tremendously, however. A person by the name of Keller, person by the name of Metropolis, the two people who actually, Clara von Neumann, for example, actually computed some of the first Monte Carlos in Eniac by programming. And when I say programming, I mean they use patch cords to link different parts of the Eniac. It was a big control board, parts of the Eniac together to do adding and subtracting and so on and so forth. It's a big logic machine. Okay, we're going to use this logic machine. It's fun? Not yet. Good to follow through. Follow this, that's all. And I'm going to call this simulation. Yeah, I'm going to call it the record of our handiwork. Okay. Now, the next thing we need to do is have developer, and you can look up in Microsoft Office how to put developer in your ribbon. And I think we did that in week 2. But here's developer, and I'm going to go to Visual Basic. As you can see, there's nothing here. I need to put something here. And the way you do this is you right-click the project and go to Insert. And you want to insert, in this case, you can do user forms, but we don't do that in this course, a module. I usually like to highlight that and change the name of the module. So again, other humanoids, other than the cerebral cortex of the Excel robot we're building here, can understand what this is. So this, I'm going to call this the simulator. See, that changes there. Now, I need to put a simulation routine in here. Am I going to program directly in front of you? Absolutely not. Absolutely not. I'm going to get another, I'm going to reuse code and copy and paste it in here. Let me go do that. So you can see here, I've opened up another project, VBA project. It's just another Excel spreadsheet. It is the week 5 simulation 1. That's what we're doing this week. Waiting time Cholesky demo. Well, the Cholesky demo's inside of it, and the waiting time simulation is there as well. And here is the subroutine. It says command. Doesn't have to be, this could be, you just write it whatever you want in here, but it has to have these two parentheses open. And I'm just going to copy and paste this directly. I don't want to have to rewrite this stuff. It took me about an hour to totally figure this out and make it work when I did do it. Monte Carlo simulation here. Let's put this into our simulator, just like that. And I've done this in so many times. I know this will work. It works quite well. Congratulations, pat yourself on the back. You could write a different message that's less snarky than that. Simulation complete. Sure, simulation complete. Cholesky demo simulation is now complete. Well, almost. And you can put in other information here as well. So that will pretty much do this. Instead of command, I will just say Monte Carlo. This is called, by the way, when you program this way with a lowercase and then the next word is uppercase, it's called camel, the hump, camel notation. Okay, if I did this instead, which is my typical practice, it's called the snake notation. Do I need click? I have no idea. I'll have to look that one up. I think I remember I needed it, but okay. Press Control S to save this. And I have to save the whole book. Let me save the book someplace I might remember where it is. We don't need that. I don't know why that's coming up. Fascinating. Okay, this is all because of the touch screen, by the way. There we go. Let's put this in. Not philosophy, demand decision optimization. And by gosh, we are in week 5, and it's in the workbook. Now we're going to call this week 5 demo. Oh, and when I do that, notice it's coming up with a result. I actually want to save this as a macro enabled. And for me to do that, I have to go back to this. Here's the demo. And then do a save as this PC. And now you go up here, you do a save as by choosing the correct designator of macro enabled workbook, which is illegal in many IT shops by corporate policy, IT policy, because VBA has been known to carry viruses. Well, join the club. So does Java, so does R, so does everybody can carry a virus. So nefarious stuff. Okay. Just tidying up here. Okay. Now, we need a button. Go to developer. Go to insert. Very first one is the button. Oh, thank goodness for that. And just put a little button right here. And it's going to instantly ask me to do something. All my open workbooks will have all of their subroutines listed. I just want this workbook. There we go. Our Monte Carlo snake snaking through here. And when I click on this and say OK, it'll connect. It'll connect that routine with this button. Now, of course, with this button, I thee wed, let's take this out and write in the word simulate to a George Gilder here. I don't know what's going to happen. I do know what's going to happen. Let me just run it and see that it does happen. It didn't, and it's the right thing. The little information up here is what's in the breadcrumb drawer at the top, and I is information. Cholesky demo simulation is now complete. Well, I don't believe anything. I want to see if it did it 10,000 times. Holy moly, it did 10,000. The average is this, 0.5. The sum is some huge number. But 0.5, yes, the average has to be 0.5. It's drawing numbers between 0 and 1. The average has to be 0.5. What's the average of the other of the z's? Let's try not the first z, the second z. That's the big correlated one. The average is 0.005. Ooh, that's different. Something different happened because of our transformation. Okay. Now we could use these as the seed for other transformations. And that gets a little tricky with what we have to do. But I just want to go back into the Visual Basic for just half a click here. There we go. I believe I want to be in simulator. There we go. Here's our Monte Carlo click. This is kind of old school programming. It's called a subroutine. If you're working for SAP in an enterprise database project or Oracle, they'll call these scripts. Same idea. You have to declare the dimension of various things, and I'm declaring 3 dimensions: R1, R2, and R3 as ranges. I'm declaring another number as a long variable integer, and yet another number which I'm not using. Why is it in here? Oh, that's from an old routine I was running. So I don't even need that anymore. I don't see any LLKs. Log likelihood, by the way. Okay, we can get rid of that. That's cool. When this runs, you notice no flickering happened. You had to wait for the result. Now we can put a progress bar in here, and that would be a lot of fun to do, but not today. Maybe not even this term. But it's not a hard thing to do. It means you have to create a user form for the progress bar. And then you have to program the user form with VBA, and it will show you the progress of the routine. So you know something is going on in the background, right? Okay, good. And it will probably have a counter in it from 1 to 10,000. And application calculation equals this. Now we set it to manual. So that means function key 9 is enabled, but every time this thing calculates, it's going to force a calculation. It's going to be a manual calculation. And so we set the range called calculation. Look at that. We have that in interface. We had that in simulation equal to R1, R2, and R3. And then we go through a 4 next loop, looping through 1 to 10,000. Now, what happens when we do this? The first thing we do is we say R1 calculate. In other words, force just that region to recalculate. The whole sheet doesn't recalculate, just that region from C2 to N3. That's it. Okay, that was our Cholesky transformation. And then it also says recalculate interface. That'll force another calculation. So we're getting randomness here. That's the idea. Indiscriminate mean. It's not random, really. Nothing's really random. The random number generator is not a random number generator. If you know the seed for it, you can predict any number out of it. Okay, get that out of our minds too. And then finally, we set range 3. So calculate, offset. Now, offset is a terrific function. It says offset 1 for I run equals 1. So we're on row 1. It says we're on row 0, actually. The offset works on a different indexing system. It says the first entry is row 0. So in our 4 next loop, we set I run to 1. It then says go to that simulation, that bar, go to the next row, that's I1, I run equals 1. And that offset is you can see is a row column. And you put 0 in for the column because you just want to move the cursor there, quite literally. And whatever's in that row, put in R2.value, whatever's the value of the interface. Then move on to the next one and then do this 10,000 times. Then set calculation back to automatic, because that's normal. We want to see things move. And application screen updating back to true. We want to be able to see the updating of the screen. And then finally a message box, and that ends the sub. So now you have it all the secrets. All the secrets here. There we go. So just going back, the routine does this. Okay, by the way, where is this? Ah, it was all of that. Okay, so it's B2 to E4. It was C2 to N3 in the example in the text there. So calculate that, recalculate this, go here, that's R3, also known as simulation. Offset for I run equals 1, go here, and then deposit this here. Okay, now it's already changed stuff around. Okay, so that's all it's doing. And then it goes through the next loop and says offset to 2. This is 0, this is 1, this is 2 in the offset business. Go here and deposit whatever is up there here, up in the interface here, R2 dot value. Okay, and then it runs. Okay, so now you have the whole story. Simulate it again, but we're not going to. Here we go. So that was richly rewarding for me. I hope you got a little bit more out of it than just reading this. So this is the routine that I ran. You see the mmult LX here, trying to give you all of the details in all of these formulas. So it basically ran this, and then the offset, boom, 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 boom. It kept going through that loop until life was over within the loop. Okay. Here's the routine. And now we go back to the robot. Now the robot, we're using these variates. So we have a bunch of variates. Okay, we use x1 and x2 as the new variates that we're creating. And the first one will just be ran. The second one, we'll see here, is a formula. It's a kind of a big formula that's required in order to transform a correlated variable into a normal variable, because that's the next trick up our sleeve that we have to perform. And so we use norm dist to do this. And notice, what is the variate we're feeding norm dist? It's this. Sorry, I maybe have confused you with x's and z's. This is like the first z, and x2 will be like the second z. I should probably put that up there like that, but I didn't for a different reason. So it's basically saying take f4, take the random number, multiply it times row, whatever row is. Row is this number right here. Oh, minus 0.7. Plus ran times 1 minus row squared, square root of that. And that's just the matrix arithmetic working out to get the second correlated variable. Now, this is normally correlated. Now, we've got that. And now we compute alphas and betas for each of the 20 eateries. Well, the first eatery is the mean of alpha, whatever that is, mean A, 3.5, plus sigma alpha, So it's a mean plus the standard deviation times how many standard deviations are we away from the mean? That's what X1 will report. How many standard deviations away? And then we have our number right here, 4.70. Okay, so it's a little bit high. Do the same for eateries in this. And now what we have to do here is a little bit different. Same idea as in H4, a little bit different style. And norm inverse is the way we use a random number and create a normal number. Now, because all of these numbers are between 0 and 1, which they are with norm dist, and by the way, I use true. True gives you the cumulative distribution. Doesn't give you the point probability, it gives you the cumulative distribution. And the cumulative distribution will be some number for a 0, 1 normal distribution between 0 and 1. Very easy, nice and easy to use. And we get the eatery numbers. Okay, the B eatery. Okay, so if it's an afternoon shift, it'll be 4.7 minus 0.97. 3.99 minus 1.14. So we can plot this, and you can see that they're negatively correlated with one another this time around. If we did this, press F9, you'll see these things move around. So now we have correlated the average, the intercepts, and the slopes, the average morning eatery wait time with the average difference between morning and afternoon. That's what B is remembering. Kind of keep remembering this. I suppose by this time you've stopped and you started again, because this is pretty thick stuff. Here's the Z2 algebraically. We take a random number, X1 times rho, plus the square root of 1 minus rho squared times another random number, and Z2 will be correlated with Z1. Okay, that's the idea. Then we get to the main course here, where we're just running. Lots of variates. So we have different runs for each eatery, and it's morning and afternoon. Now, there's a way to make morning and afternoon repetitions. I don't explain that here, but the average wait time that we can compute is an index match function. Please look at that. And we can use an F statement too. There's a lot of tricks inside of this. As a matter of fact, there's so many tricks. Let's look at one right now. Okay. So that's it, longhand here. I suspect if I did this, there we go, see? It made the sheet recalculate itself. Okay, lovely, enough of that. Stop that nonsense. And here's a live simulation with some notes over here. But look at this. I start out with 1, 2, 3, 4, 5, 6, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then it starts all over again. Now there's a way to do that, and I'll explain that sometime. But the other thing that we do in this routine here is I also randomized the in the robot. the timing of AM and PM. So if the random number is greater than that probability, let's say it's 0.5, draw a 0. Otherwise, draw a 1, a 0, and a 1. That makes this random. Now if I add these up, if I add, see how many afternoons. Oh, 1,017 afternoons. Well, how many of these are there? I did 2,000. Now, I didn't use VBA to do this part of it. I did it for the demo for correlated Z's and the L and the X and oh my. But I used that same technology to produce the alpha and the beta. And here's how it works. Here's the alpha. I called this array A eatery. And this array B eatery. It's in a table with an eatery ID. Okay, here's the eatery ID, 1 to 20. Okay, here's the morning or afternoon. It's an afternoon. Now we want to do the average. We're back to our basic equation. To compute the average. Okay, so we compute the average. Look at it. Index. Let me put it in here. It's a little bit easier to see. There we go. And let me open these sluice gates up a little bit. Okay, the mu again. Okay, now you can see it a little bit easier. Go to A eatery. For eatery 1, find the row. That's what match does. Find the row in the eatery ID table. I have a table over there. That whole thing is a table. Do an exact match. Find that row. Okay, in that row, find the value of E eatery in that row. That's probably row 1. Add to this. So this gives me the right alpha for the right eatery. And now we need the right beta or B eatery for the right eatery. We use index match again. Now, I use index match instead of V lookup or H lookup or lookup because the shape of tables, it's easier to get a query out of a shape of out of a table of any shape, whereas V lookup, I have to have a very specific shape. My lookup has to be in the first column, literally, the thing I'm querying, and I have to know the number of the column. Okay, here it doesn't matter, and the lookup in V lookup is looking for, it's going down and doing exactly the same thing. It'll look for eatery 1, eatery 20, eatery 5, and compute the row, but it has to know what column. I don't need that here. Okay, it's a lot easier to do this here. So I have eatery ID, match this, and multiply it times. Okay, so I'll changing every time. This number. Okay, and I have mu. And then I can simulate, because now I know what is mu, and look at the simulation. Wait times are simulated, the sim symbol there, normally, with a mu and a standard deviation. Now we're going to let the standard deviation be the same across all of the eateries. Now that's something we can change very easily, but we're not modeling standard deviation this week. Next week we may need to model standard deviation, but if you look over here, I have as an entry sigma weight. Okay, I can make this whatever I want it to be. Matter of fact, you see it's called sigma. It should be called sigma weight. That's all right, it'll still work. And so go back to the simulation live here. Sigma weight. And it will take F3 and add something to it. It'll add a distance from F3, either positive or negative distance, norm inverse rand. Okay. Now the correlations are already in here. They're already buried inside of those index match lookups of correlated A's and B's. That's a tremendous technological innovation for us right there. But if we just want to see what sigma weight is, okay, it happens to be that number, same number. And then we multiply it times inverse. Now we have to feed norm inverse. Look at that, that happens a lot. Touching something that shouldn't be touched. We have to put in a probability. Well, a rand 0, 1 will give me a probability, a cumulative probability from 0 to 1. And then I have to specify the mean as 0, the standard deviation as 1. This is called the standard normal or standard Gaussian distribution, z-scores. And I get that number. So that's the additive. That's the additive to mu, which already has the random correlated variables in it, the alpha and the beta. So that's already there. Now we have to add a little stickiness to it. We get this. Okay. So that's how that works. And the next trick up our sleeve is EDA. We want to get that picture. And this is how we get the picture. Okay, we create a grid. And with intervals, I'm making a 21 interval, basically a histogram. There's a beginning, which will be the minimum of the grid. And there's an end. It's the minimum plus the width. And basically, we're using non-overlapping intervals for what's their wait times. So we're doing this again. Mu sigma. We're simulating all those wait times. We're taking a sample of that again. Okay, that's we just had all of those wait times, and now we did that, and now we're looking at intervals of wait times. So we have a min less than W less than in this case min plus width. Now the convention is we start here and go up to here. Okay, that's a typical convention. And then we find the midpoint as well, just the average. We go to the second interval, and that's equal to the end. The beginning of the second interval is equal to the end of the first interval. Okay, then we just keep cruising down. Beginning is equal to the end of the previous. Add width. So these are all equally spaced. Each one has a midpoint. That allows us to do the plotting. And then the next trick up our sleeve is to use count ifs. Now, Winston has a lot of information on this. You can look at that and play with it. But basically, there are two logical pieces here. And actually, what I'm doing this, doing the min less than or equal to W less than that ending min plus width. Count ifs allows you to put multiple logical statements here. And I'm also using another thing called indirect. Indirect of C3 goes to a named range in C3, wherever that is. Oh, it's weight. And that named range, not there. It's here. And if I go down here and look for it, a lot of stuff in here I don't need. There we go. That's the named range. Okay. So go to that named range. And whenever it is true that a weight is greater than or equal to the beginning, in this case, 1.31, count it. And it's also true whenever it's less than, this is a both and statement, both this has to be true and this second one, it has to be less than the end. There are 13 where that's true. Okay, this is logic. Logic. Truth statements. A both and truth statement gets us the number of weights, the number of times we see a number between 1.31357 and 1.55041, which are weight times in minutes. There's 11. There's 13 of them there, 12 here. There's one here. There has to be one because you have to have at least 0.83998 because that's the minimum of the weight series. Then it goes all the way up. Look how it bounds up and comes back down. So we have a preponderance of combination of weights in the middle here, and far less frequently occurring ones in the tails. Classic normal distribution. We do a relative frequency. Okay, we do a relative frequency. The count of weight, how many are there? There had better be, this better add up to, it adds up to 2,000 because please notice this one, 5.81 is the max in the weight. We have to count it. And so that last one isn't less than, it's less than or equal to. That's a boundary condition. And we have the relative frequency here, which is frequency divided by the sum, which are 2,000 of these things in simulation. And then we do a cumulative relative frequency. We want to know that too. That's called the ogive. It's equal to relative frequency in the first instance, and in the second one, it's equal to the previous plus an increment. Well, 0 in that case. Okay, let's do a little better one than that. 0.7007 is equal to 0.0005 plus 0.0065. It's an accumulation. You're actually calculating the area underneath the relative frequency curve. You're doing numerical integration effectively with this. And then we have the Gaussian for comparison. And look at how we do the Gaussian. We take J4, which is the mid, calculate, oh, no, dump in the mean of the weight and the sigma of the weight, and say true. True makes the cumulative density function, the CDF. Then we go ahead and plot. And of course, the plot setup uses weight times. I can write these in. I could refer to another cell as the title of, and we need a primary and a secondary axis because we have two different scales. We have a 0 to 1 scale over here for the ogives, and we have a much much smaller scale, 0 in this case to 0.14 for the density curve. You can see we got all of these. We got 21 points here. That's why it's a little bit rugged. But look at the cumulative. It's very smooth. And we tend to see ogives in front of clients rather than densities. I like them both. Put the, as a matter of visual real estate here, we put the legend, always put a legend. Always put names like this so that we know what's going in relative frequency, cumulative relative frequency. And I like to put in the dimension here, minutes. Into the axis labels, we have a really interesting title, which brings in data from the simulation itself, the number of eateries, the number of visits, all of that. So we have 10 for each of 20 eateries. That's what visits for that. As a matter of fact, I probably want to write that in. Number of visits. There we go. And you can see that allows us to edit dynamically. There. Took a couple of seconds for that to happen. Okay, that was a recalculation. Notice the curve shifted a little bit. And can I use a static RAND? Yeah, I can build a static RAND so it does it once, one and done, and it doesn't, we're finished. Okay, 10 visits for each of 20 eateries. And now we have a distribution of waiting times to talk about. And with this, we can go down here, use this graph to point to a typical John Tukey 1977 exploratory data analysis, which always has a min and a max, percentiles, usually quartiles. These are quantiles. I could make this 0.05. The 50th. And that makes this, what? Won't be 0.05, be 0.95. That's cumulative probability too. And now I have an interquantile range instead of quartile. I have a mean and a standard deviation. Now notice what's happening with this particular one. Oh my gosh, a little crazy here. Let me put this over here so I can see it. Okay, yeah, okay, every time you do this, it changes. Yes, it does, because we have a volatile RAND function in there. And I got mean, standard deviation. The mean absolute deviation is probably the robust figure we want to use here for scale. Scale is, look at this, IQR is crazy. That's a big IQR. It's not comparable at all to these scale measures. And skewness near 0, and kurtosis +3. You have to do a +3 because if you don't do a +3, it'll be near 0. It does what is called excess or net kurtosis. It takes 3, which is the normal curve, and subtracts it from the raw kurtosis. So I always add it back. So I like to see the real number, and it's very close to 3. All of these things indicate symmetry. It's not skewed. Tails. Well, even with this little widow speak here, all right. It's like a mountain here. Let's just do another round. There we go. There we go. I mean, it's always going to be there. Fine, fine, fine. Run this 20,000 times. It looks like a normal curve. Okay, so this is the EDA that we can use. And now we're ready to analyze. So the question, okay, what is the average wait time? It's 3.35 in the simulations with a standard deviation of 0.75 across all day long. It behooves us to split this sample up into morning, A equals 0, and afternoon, A equals 1. That would be a great thing to do on the weekend. Split it up. I began that process in the spreadsheet, and move this back up here. I'm starting to make a dent in it over here. These are all frozen numbers, because you need a frozen number. That is to say, a paste. This is what I mean by paste. Control C. A paste values. That takes a frozen version. You don't get any formulas or anything, and it's there forever. It's there for posterity, at least till somebody gets rid of it. Okay, and this is a PM version. Now we do VA on the PM version. Well, kind of interesting. Instead of taking that from simulation live, I can create a control that will have weight PM, weight AM variables in it. I can install, is this too much right now? Yeah, probably. I can install here a list box. How do I do that? Data. I need validation. There it is. That's the validation, data validation. And I go to choose something from a list. The source is in the control, and it's one of those three. I say okay. And if I do that, I don't know if this will work. I haven't tried it yet. It does work. That's what the AM looks like. The AM is 3.37 with the standard deviation. What does the PM look like? 2.94 with a different standard deviation. We get two different distributions in this simulation. And now this is what's interesting to decision makers. We have a difference. We have potential resource differences. This is a vaccination site instead of an eatery. Well, it's the same kind of problem. How much food do you have? How many staff do you put on? How many vaccines have to be, if it's Pfizer or Moderna, have to be thawed out and held for so long, only 2 hours in a refrigerator, et cetera, et cetera, et cetera. How many sharps do you need, the needles? How many credentialed people do you need? Trained medical staff. How many guides do you need? How many police do you need for security? We want to make it a secure facility. And it goes on and on and on. You have a 15-minute waiting period for the vaccination. You have an area for that. And you have to fill it up, and every 15 minutes, empty that area. How big should that area be? Another issue, okay? All possible in spreadsheet modeling like this. I'm going to leave you with that. And that was the exploration, hands-on, of this. But I just did something that's not in this, and that's put a list box in. Try it. Here's some further words, count ifs, and the wait times, and the next steps. I already did the next step. Analyze morning versus afternoon. Okay. Good article, the Eniac. It should have been two N's there. It's that is correct. IEEE Annals of the History of Computing. Try this computation down below. John Tukey's book is right here. It's been archived. You can pull it up. Excellent resource. Excellent resource. We all have one. All right, I'm going to leave you with that after a very, very long session. Very long, perhaps too long, but I hope it's useful to you. And again, thank you very much for your very kind attention. And see you on the other side of this weekend for our final big push on simulation. We're going to do loss calculations there. You're going to be confronted with a new distribution that you may not have heard of called the generalized Pareto distribution, which has just two parameters in it, just like mean and standard deviation. Not quite. And away we go. Take care and have a great weekend. Thanks very much.